what we're going to look at now is the concept of time complexity of an algorithm, to examine if an algorithm is basically efficient or not. So for example, in this case here, the x-axis represents the number of cities, and the y is the number of basically the time steps that the algorithm, T of n, that's the time steps, how many steps the algorithm is taking to output the shortest path. So you can see if we're using the exhaustive search solution, okay, that the time will be in the order of n factorial, which is the algorithm basically computationally explodes. It will not converge if you give it, for example, 1,000 cities. Okay, so you'll wait for a long time to have the results. Now, this is the key question we're going to look at right now. How to compute. So remember, we have our inquisitive bee always asking questions. So the question is how to compute time complexity of an algorithm A. So what is time complexity? How can we possibly evaluate or examine the running time of an algorithm? Is it efficient or not? How can we quantify it? So a first maybe thought that comes to our mind is using the running time, the duration of the algorithm, in terms of milliseconds. For example, you're using your personal computer, you're running, let's say, the nearest neighbor solution to the TSP problem, and then you're giving it 1,000 cities or 100, and then plotting the time, seeing how much, how many minutes it's taking, etc. So do you guys think that this can be regarded as a universal way of evaluating the behavior or assessing the behavior of an algorithm? If let's say all of you right here have different computers, okay, and you're going to run the same algorithm, okay, and do you think that all of you will get exactly the same time in terms of, I don't know, milliseconds or seconds? Do you think that all of you will get exactly the same time? No. Why is that? Because, what do you think? Because it depends on the machine, right? It depends on the machine you are using. And also it depends what? On, yes? Oh yeah, so. Sorry, I didn't hear you. What did you just say? You want to say?
I want to clarify different aspect.
A different aspect. Go ahead. So what is a different aspect? Yes?
I think it's very hard or impossible to see what the complexity before running the algorithm, just looking at the source code. So it's not a good you cannot evaluate the complexity just by looking at the source code.
You can evaluate the complexity by just looking at the source code, or you cannot.
You can't if you use this one.
You cannot. Very good. So what you're saying is, if you look at the algorithm, so you have an algorithm, right? And you're waiting just for it to input it to a computer and see how much time it's taking. That's not a good way, because first, you're just going blindly, which means you're shoving it into your computer, running it, and getting some time. But this is not good, okay? Because first, you can look at the algorithm and we try to come up with some tools that allow us, by analyzing the instructions in the algorithm, to determine or find its, complexity, or it's the time, estimate roughly the time that it will take to run on the input data, okay? So that's the ideal solution, or a good solution to this. But if we were not to do that, then basically it will depend on the machine, it will depend on the data we were giving to the algorithm. So all of you will get different results, will get different times, and in that case, we cannot say that this algorithm runs, for its duration is 2.5, I don't know, to 1 milliseconds, for example, okay? We cannot say that, because each one of you will have a specific duration or running number. So this solution is actually not good. We cannot rely on just the physical running time. Okay, it's the other way around. Okay, so this is not good. We cannot rely on this to evaluate the behavior of an algorithm. Now, how about we try to analyze algorithms, okay, without depending on the inputs or the machine capacity. And this is what we will learn today. So we will try to look at the algorithm instructions, and by looking at that and analyzing the different steps that the algorithm is taking, we can look at what we call the running time t of an algorithm in terms of the steps it's taking, okay? And in this case, this will be basically based on looking at the algorithm and analyzing how many, basically deriving how many steps it's taking to run, okay? So let's look at this. So we can have many algorithms. So for example, I'll give you an example, but here in an algorithm, we have different statements, right? So an algorithm, for example, can have comments. So these comments generally, will the algorithm run them? Will it take time to run them? No, right? So that's a 0. Then for all assignments, like for example, if A takes, here gets assigned 12 as a number, it's considered as 1 step, okay? All assignments, it takes 1 step to assign a variable a specific value, okay? Then also all basic arithmetic operation like, addition, subtraction, multiplication, division, etc. These are also considered as 1 step. So if I do this, A receives, for example, 2 plus 3, I'm just saying, this is considered as what? As a single step. So the algorithm will just run this line, and it takes 1 time step, okay? Now, if I do, for example, n divided by 4, okay, x receives n divided by 4. So this is assignment and also an operation. So also this is 1 step, okay? And these are basic steps that an algorithm can include, and these are the simplest ones. Now there are the most complex ones that we will learn about during this lecture, and especially in the next lecture, which are the for and the while loops, okay? Now the for and the while loops, there are some rules on how to determine the number of steps for each of those, and depending on the limits, like how many times you're looping over your variables, we're gonna be able to find the number of steps, okay? So the other ones are very simple. So let's look at, for example, if we have an algorithm here, in terms of time complexity, we will look at different cases. So when we analyze, yes?
Sorry for interrupting your speech. While we're saying time steps, are we mentioning like a mission cycle, or what's the time step?
A time step is just, for example, I'll give you a detailed example in a little bit. It's just, an instruction that the algorithm is running only 1 time, okay? So it's reading, for example, if you have, I'll just go forward. So this is, for example, this is an algorithm, right? It's quite simple. It's adding up numbers from 1 to n, right? So here, a time step is like how many times that algorithm, will the algorithm run that instruction, and how many times, okay? So will the algorithm run this instruction? Yes, it's not a comment. How many times? Here, starting from here, from instruction 0, this is my algorithm. It will run it just 1. Okay, how much time it takes to run that depends on the computer. It might run this assignment, it basically is storing 0, like in variable C. It might take, I don't know, 0.0001 seconds, okay? It depends on the machine. We're not talking about like the specific physical time. We're talking in terms of the number of instructions and how many times that instruction will be executed in the algorithm, okay? So that's exactly what we mean. So I'll give you more examples in a minute for you guys to understand better. So in terms of time complexity, so we have an algorithm A, and usually we have 3 scenarios that we will learn to, look at basically. So for an algorithm, we can compute what we call the worst case scenario. That's the worst complexity. And we are more interested in this one because when you when you design an algorithm, you want to learn its worst behavior for the worst, data scenario you're giving it. So you don't want to look for the best case. You want to look for the worst case because you want your algorithm to be successful whatever data you're giving it, okay? So the worst case basically is the maximum time of an algorithm on an input data of size n. So let's say your algorithm takes n cities. So T of n is the time that's taking, like in terms of like number of steps here. And it's the maximum time that will take, so that's the worst case. The average case, it means that most of the time, this is the average time complexity of your algorithm. So most of the time your algorithm, it takes, for example, let's say not n factorial steps, but it takes only n steps. So we're going to see these different examples, but I would like you to keep in mind that for an algorithm, we can have a worst time complexity, an average time complexity, and we also can have the best case or the best complexity, and this is actually using a slow algorithm that works fast on some input, which means sometimes you're lucky because you've given your algorithm the right the easiest data set for it to run very fast, right? But if you change the data set, it's gonna just explode. It worsens basically. Okay, so these three different analysis we will learn about. So we can analyze an algorithm, look at an algorithm, and try to find its worst, average, and best complexity. But sometimes these are equal, which means whatever data you're giving to your algorithm, the time complexity is the same. It's always roughly taking the same time, okay, same amount of time. So here, let's look at this example. For example, the for loop. How can we count the number of steps, right? So in this, this is like an important rule for you guys to remember because we're going to see for loops in many algorithms. So here, if we're looping from, I equals to, starting with n to m, right? So the first index, so we're going from n to m, counting numbers, right? Of course, m is larger than n, okay? So the easiest one is usually, guys, you are familiar with, I from 1 to n, right? Let's start with this one. How many times we will execute this instruction, just the for one, okay? How many times we will execute it? An algorithm will execute this instruction if we look only at this one. This is counting the number of sets from 1 to n. So there is a rule. So it's n minus 1, and there is plus 1. These are the number of sets. Like if you're counting from 1 to n, these are the number of elements from 1 to n, basically. So how many elements we have? N times, right? So here we're going to run this instruction, the for loop, n times, okay? But there is another thing. So for an algorithm, when in your computer, what your computer is actually doing, it's counting from 1 to n, right? This is the beginning of the for loop. But then to exit the for loop, it needs to also try I equals to n plus 1. Otherwise, it will keep looping, right? It needs to know when to stop. So when I basically, if you're incrementing the, we're incrementing the I, right? When I takes n plus 1, it just exits the loop. So there is also an extra step that the algorithm will run to exit the loop, and this is we call the exit step or time step, okay? So in this case, if you look at this algorithm, how many times it will run? This one. So there is we apply the rule. So how many items, let's say we have from m to n, it's m minus n plus 1. Okay, so this is the number of times the instruction will run, plus another one to exit the for loop. So the algorithm needs to go over the boundary to know I'm not within this range. I have exceeded the m. So now I need to exit the loop. So it's going to just skip over and go to the next instruction that is here. Okay, so plus 1. So this is actually the number of times that this instruction is being run. So this one I can write it T of n just for this line, okay? m plus, well, of course we have two variables here. It's a bit complicated, so let's start with this example. These are two variables plus, well, plus 2, right? Let me just write it correctly. Sorry, guys. Okay, so m minus n plus 2. Okay? And then what about the instructions here? How many times we will run them?
Same thing.
Okay, so just based on the m and the m, I want you to think in an abstract way. Okay, so how many times I will run this? The instructions inside the loop.
Just the same amount. The same.
Yes, the same one, and we don't have the exit, right? So I will run it m minus n plus 1 times, okay? So this is, rule number 1 you guys need to remember for computing time complexity. Next, we're going to see the while loops and the if loops, and these we need to distinguish between two cases, while it is true or false, and if it is true or false. So to wrap up, let's look at this. So here, the loop call for from I equals to from I starting with n to m takes m minus n plus 1, okay, times plus another one. So these are like the number of steps, where an additional time step plus 1 is used to exit the for loop, okay? So the total number of times for loop is called is m minus 1 plus 2, and that's what we have just computed. So the instructions, on the other hand, inside the for loop are executed exactly m minus n plus 1 times, okay? Great, now let's apply this to this algorithm. So you guys, I'm going to give you 1 minute and you can apply this rule. I'm going to show you both so you can apply it, okay? So tell me, what should I write? How many times each step is run? So let's say the total number of times here. So first one, second one, third one, and last one, okay? Pen and paper, think, or mentally, all is good. Okay, so this tiny algorithm, what does it do first, this algorithm? It produces the sum of digits or integers from 1 to n, right? Very good. Now, this is just summing I from I equals 1 to n. Okay? Now, the first line, how many steps to do this? Like, how many times it is executed? 1, very good. The second one, the second line, like this one, n, right? So we have, oops, n plus 1. Okay, so for the exit test, and then the instructions, number 2 is n, so there's no exit test, that's inside the loop, and the last one is just returning, so that's 1. So now you guys know how to compute the time complexity of this algorithm, like just simply. So here, if we add up all the steps, so here it's like 1, n plus 1, n, n1. So the total number of steps, if we add them all up, it will be, let's add them all up here. So we can do an addition, so add them all up. So it will be 2n plus 3, right? 2n plus 3. And this is what I was talking about. This is how we compute, basically estimate the time steps of an algorithm. It's in function of n, the size of the input variable, regardless of the computer you're using and the resources you're using, okay? Now, starting from this, we're gonna go one step further and see how to analyze this. So this is, there are lots of constants floating around, like 2 and 3, okay? But what matters is this variable, the n, okay? So we can say that generally this algorithm runs in the order of n, and we will learn this later on, in the order of n. So this is, the vocabulary we'll learn. So in the order of n, which means that these constants generally, they do not really matter. All that matters when n becomes so big and you plot it, right? This will take over. So this, constant is very important. Now, what you have here in function of n is important. You might have, sometimes n squared, you might have n factorial, 2 to the power of n. So you'll have different things, but the most important thing here is that your n variable, okay? So how to compute the time steps of this algorithm? Let's look at this algorithm, and you guys will do it. We will do it together again. So this is, what does this algorithm do? It's also simple. It sums the, actually it's the same one. But here I drew this table, and this table is a more formalized or organized way of computing time steps. So we have an algorithm. And in this algorithm, let me just choose another color. So here, actually, the definition of an algorithm is just how many times it will be executed. These will not be executed. These are just empty lines. They're not like really executed when you have an algorithm. So these take 0. Now, for this one, we have steps and we have frequency. So I have basically separated them into 2 columns. This is, how many, how many times like this, basically, will this instruction be executed or not? Yes or no? Okay. And if it will be executed, then how many times it will be executed? So here, for example, for the first one, this line 3, it will be executed one time, okay? The other one, we have a for loop. And this one, a return is also, it will be executed. This one, it will not, okay? So this is simple, but what matters, what we are really interested in is the frequency. So how many times I will run this instruction? Okay, 1 time. And the second one, how many times? N plus 1. N, okay? And then the last one, 1. Now we will multiply. So basically it's, we count the total number of steps. We take the step or execution, if it will be executed or not, times the frequency, and we will get the total number of steps. So by just multiplying these, we're going to see why this is nice and important when it comes to complex algorithms. This is a very simple algorithm, okay? So we'll have it's quite simple, 1, n plus 1, n 1, and then we're going to have 2 n's plus 3, and this is the total time, okay? Great. So now, after looking at that, let's look at how we're going to analyze the behavior of this algorithm. And we will look at what we call the asymptotic notation, okay? So we know up to this point that the time, the running time, or the number of time steps for our algorithm A, computing the sum of the elements of an array, is in the order, is basically 2n plus 3. Now we are going to analyze the behavior of this algorithm. So how to do that? We will look at what we call the asymptotic behavior of an algorithm or function. And this asymptotic means when we're looking at the algorithm behavior for a very large n. So this is basically the limit of this function. So here we'll look at how this function behaves when n grows larger, basically when our n tends to plus infinity, okay? So for example, this is what we call also, before we go into these examples, this is also what we call the order of growth of the running time Tn of an algorithm. And it is defined as the highest order term. So I'll explain. So for example, if we look at Tn right here, we have Tn is equal to n to the power of 3 plus 3n. So what is the term with the highest order here? Like the n term. It's this one, right? The highest order is 3, right? So what we say that the order of growth of this function, okay, it's in the order of n to the power of 3. So asymptotically, when n grows so large, becomes very large, okay, it means that generally if we plot this function, we will see that when n grows larger, so it might have some, like fluctuation here, but at the very end, this is just, scribbling, it's not the real function, but at when n grows so big, it will be so close to n3, okay? This is what it means, basically, okay? So here, we have another example. So let's look at Tn equals 2n plus 150. So in this case, what is the highest order we have? It's just n, right? So in this case, we say that Tn is the order of growth of Tn is in the order of n, because that's the largest variable we have. Yeah, you guys have any questions? Okay, so now let's look at another example. So in this, we always, when we compute the order, when we want to derive the order of growth or the asymptotic behavior of a function, we completely ignore constants. So constants, they do not matter at all. Okay, we don't look at them. They're like, we can ignore them. Why we ignore them? Because if you plot the function and when n grows to infinity, you will see that at the limit, these constants do not matter. What takes over is your n. When your n is, for example, 10 to the power of 9, that's what really matters. So these constants become negligible in this asymptotic space. Asymptotic space, let me just draw it here. So asymptotic space, it means when your n becomes so large, okay? So this is what we are interested in. Why we are interested in this, sorry, okay, let me use another color. Why, guys, we are interested in this space? Anyone can tell me? When n grows very large, becomes like when we have a large input size. Any ideas? So let's say, for example, why we are interested in this, basically when we're running an algorithm, looking that this algorithm maybe is like, has its number of steps is n cubic plus 3, and the other one is 2n plus 150. Why we don't just look at it that way? Why we are interested in examining the behavior of this function, its growth, when n becomes very large? Why we are doing that?
Because that's when it takes the most time.
Yes, and that's why also
Visits. So we don't want it to take
a lot of time, right? So very good. So sometimes you might find a function, let's say if you find a function like this, constant equals to 1, it means whatever you're giving this function, right? Look, guys, if I give it, I don't know, like, 1,000 or 10 million, my time is always constant, right? This is ideal. But imagine if, like, you have something like this. So you start with a small number, so it's quite constant, but then when your n becomes larger, it just explodes, becomes like, the time becomes, grows much faster, right? So our goal is that for algorithms, usually, we don't only have a small number of, like, we don't have a small size data set to work on. We want our algorithm to work on large-scale data sets with billions of points. If you were, for example, to detect groups, like to cluster Facebook network into different communities, into different groups where people share the same interests, your algorithm will explode, right? It depends on what kind of algorithm you're using, but you have a large, number of users. You have a large number. Your n is very large, so your algorithm. If you have a very good time complexity for your algorithm, we don't look at small numbers of n. It might survive when you give it 10 items. It might survive when you give it, maybe hundreds, but when you give it, like thousands, it will explode. So this is why we call it, when we look at time complexity, we are interested in the asymptotic behavior of these algorithms, okay? So we also, so this is what I mentioned before. So we ignore the leading terms constant coefficient because these are not important, and also the lower order terms. So the lower order terms, for example, what is the highest order of n we have in this function t of n? What is the highest order? N squared, okay? So we're gonna ignore all the lowest ones because when n grows bigger, this will not matter. The constant will not matter. So all that matters is this n squared, okay? And this is why we say that t of n, it grows in the order of, n squared, okay? So it's like a polynomial, okay? Now, these are different complexities that you guys would like to look at and know. So we have, for example, the plots of different functions. You can visit this website. It has a lot of good resources about time complexity and nice visualizations. So here, let's start from the best time complexity to the worst. So this is the best, right? So the best is what? It's constant in the order of 1. It's constant time. Like it does it in, like basically it's almost constant, the time that your algorithm takes. And the worst is in the factorial order. We have exponential, we have quadratic, we have n log n, for example, n log n. And you can see all these plots. So here we have plotted all these functions. So this is n log n. And when you compare n log n, right, something like that, with the polynomial one, which one grows faster? Which one is worst when you guys compare these two? This one, because it lies above it, right? So it's much faster. And then this is even worse, and this is even worse, which is like the factorial one, right? And the one that is really quite good is in the order of log base 2 of n, okay? Logarithm of n. So this one, it means if you have algorithms that are running in the order of log n, these are great algorithms because they run in almost a constant time, okay? It's almost constant, okay? Great, so here, let me explain more. So we're going to look at the big O notation in more theoretical, on a more theoretical level. So how do we define this mathematically? So imagine that we have an algorithm. So this is our algorithm, right? And then we're going to define Tn is the total sum of all running time costs of an algorithm. Now for a given, so this is just, you know, what we have seen so far, right? Now let's formalize this mathematically. So if we have a function g of n, we say that the order of growth of g of n represents the set of functions f of n such that all these functions, they lie below g of n within a constant c. Okay, so this is the mere definition. So the order, the fn here in this example, we say fn is in the order of g of n if basically we find a constant c and an index or a number n0 that is positive in such a way when n is larger than n0, fn is always lies below gn multiplied by a constant. So let's look at this case. So for example, here I have plotted c times g of n. So this is the curve I have. And if you look at this, how can we visualize this, guys? How can we plot it in terms of limit? So it means that our function, we have a function fn, it might behave randomly. It might be above, like it might be greater than c of g at this point. So it's greater, something like that. And then maybe another time, okay, it's not good right here, so I do it this way. And then starting from some point n0, okay, for all n's that are larger or equal to n0, right, my function f of n will be what? Smaller or equal to c times g of n, right? So in this case, we say that the function f of n is in the order of what? Of g of n. So this is actually what we call the upper bound of this function, which means if we have a running time of an algorithm and we can bound it by this by a function that we know, like, you know, quadratic, logarithmic function, we know that our algorithm will always run. In the worst case, it will be, you know, close to this one. It will be in the order of g of n. And this is what the mathematical definition of order of a function means. Okay? So we will look at other different examples. So in this case, we say that fn belongs to O of gn. Actually, when we say here, as I mentioned, so here we don't say this one is commonly used in many textbooks, but actually it's not equal. It should belong, because you can have why it should belong to the order of gn, right? Because basically we can find many functions that do that. Like we can find different functions. This is another n0. And then there is a set. It's actually a set of functions that satisfy this property, that are less or equal than cgn, right? So the right notation is belong to O of gn. But for simplicity, in this course, we're going to use the equality. Okay, great. So what does this mean? So let's just say it again. So this is actually the asymptotic upper bound on f. So this is what we call it. So this is the asymptotic upper bound on the function f, right? So our function is bounded, is limited by this function. So which one is worst here in terms of time complexity? Is it g of n or f of n? Which one is worst? G of n, because it lies above it, and also that's why we call it the upper bound. So in the worst case scenario, your f of n will be so close to g of n. Yes?
It's not the g of n that lies above, it's c times g of n.
Yes, very good. Yeah, c times of g of n. So here to some constant. So the constant, we play with it, but that's a very good remark. So here, the c of g of n is like, you know, our orange curve that lies above f of n. So within a constant. So the constant is important. Good. So here, let's look at this example. So what do you guys think about this? It's quite simple, right? So the constants, we say the constants do not matter. So this is, you know, the highest order. So f of n is in the order of n, right? So let's look at other examples. What if we have something like this? So f of n is equal to 4 to the power of n plus 5n to the power of 9 plus 1000. What is the order of this function? What is the term with the highest order that will basically, when n tends to infinity, it will take over this function?
4 in the order.
Yes, this is, you know, c to the n. This is exponential. So it's in the order of 4 to the power of n. Okay? Now, another example. Let's say n plus log n. So this is when we say log here, guys, you need to remember this is the natural log base 2. Okay? So if you guys look at this, which one is worse, n or log n? N. So in this case, this is in the order of what? Of n. Okay? Great. I think you guys have an idea, like just an overview of time complexity today. And these are the asymptotic classes. We're going to, you know, see many of them during this course. It's important to remember these classes. So what we have, let's look at them quickly. So we have the O of 1, which is the constant time. We have O log n, which is called the logarithmic function. So these slowly grow. These are slowly growing functions, almost in the constant time. We have linear. So O of n, we call it linear. Okay. N log n, superlinear. N squared, quadratic. Cubic. This is, you know, basically polynomial 2. This is general polynomial. So quadratic means we measure the cost of looking at most of all pairs of items in n element array. So we're considering, you know, pairs. We're looking at all possible pairs in an n element set. cubic all triples in an n element array, polynomial of order m, it's m side subsets in an n element set, right? Then we have exponential, right? And factorial. So these are the different classes. We're going to look at different algorithms in this course, study their complexity, compare them, and see how they behave asymptotically. So great. So we started from the problem of TSP, defined algorithms. Then from algorithms, we looked at how can we possibly examine their behavior, talked about using the exact running time. It turns out not to be good. Then we looked at the steps, came up with running, steps, like how many steps the algorithm would need to run. And then looked into the asymptotic behavior, because this is exactly what we're interested in. When we have a large number of inputs, how will our algorithm behave? Okay.